Hello everybody. In this video, I will give you an overview of all of natural language processing. Here I have pulled up the ACL conference, one of the biggest conferences in NLP. ACL allows you to submit to a broad range of topics here. There is a total of about 20 to 30 of them. And in this video, I'm going to go through all of the topics one by one and give you a short summary of what it is about and what is some interesting research in each area. And I will go from the least popular to the most popular. So here they've released a bunch of statistics on how many papers were submitted for each track and how many were accepted to the conference. This year, around 4,500 papers were submitted to 24 tracks. My name is Bai. I'm a machine learning engineer and a PhD in natural language processing. And let's get started with the first one. First up, we have Phonology, Morphology, and Word Segmentation with 21 submissions. Phonology is the study of how words break up into phonemes, which are the most basic units of speech in a language. And it deals with questions like phonetic transcription or investigating the sound structure of a language, for example, by identifying minimal pairs of words. Morphology is a study of how complex words break down into smaller components. In some languages, like Turkish, words are very long but are made up of much smaller units. Word segmentation is important in some languages like Chinese that don't put spaces between words, so a process is needed to separate the words in a sentence. So this track deals with the scientific study of these features in language as well as tools to perform these tasks. Next up, we have linguistic theories, cognitive modeling, and psycholinguistics with 38 submissions. And broadly speaking, these aim to connect NLP with linguistic theory in some way. This is personally my favorite topic in NLP because it is what I did my PhD in. Linguistic theory is usually not used to train models in NLP, but sometimes neural networks can be used to gain some insights about syntax of sentences or how language is acquired. And additionally, a lot of papers in this topic use experiments from MRI scans or eye tracking experiments. And they often try to compare how do language models read a sentence and compare it to how do humans read the same sentence. Next up, we have Discourse and Pragmatics with 52 submissions. This topic deals with linguistic information that spans across multiple sentences. One big problem in this topic is co-reference resolution, which is determining for pronouns like he or she which entity in previous sentences it refers to. Another aspect of discourse analysis is conversations, for example, a debate between politicians. And researchers are interested in analyzing when is a politician make a claim or a counterclaim, a rebuttal, a deflection, or so on. Next is Ethics and NLP with 54 submissions. This topic deals with issues of bias and fairness in language models, such as gender. For example, many models will assign a higher likelihood of men being a doctor and women being a nurse. Bias can occur in gender, in racial minorities, religion, and other marginalized groups as well. Language models also tend to amplify biases in the real world so that the probabilities assigned by the language models are even more lopsided than reality. Researchers in ethics and NLP try to study these biases and invent methods to mitigate against them. The next topic is Lexical Semantics with 54 submissions. And lexical semantics basically deals with meaning on the word level. For example, constructing a vector that represents the meaning of a word. This can be challenging because words in a language might have different meanings depending on the context. Polysemy is when a single word has multiple meanings, like the word note on the piano could also be a note, like in a notebook. Another tricky issue in lexical semantics is how to deal with multi-word expressions like the exam turned out to be a piece of cake. Researchers in lexical semantics try to come up with methods that accurately represent the meaning of words in different contexts and multi-word expressions. Next, we have syntax, including tagging, chunking, and parsing, which has 69 submissions. Within this category, we have several different tasks that all aim to understand the structure of language by breaking it down into smaller pieces. First, part of speech tagging tries to tag each word in a sentence with a part of speech, like noun or verb or preposition. Constituency parsing creates a tree out of a sentence where each subtree is called a constituent. Dependency parsing is the most common type of parsing nowadays and treats the sentence as a directed graph, where each word has exactly one edge pointing to its dependency. Another type of grammar is combinatory categorical grammar, CCG, which is based in mathematical logic. And researchers in this area explore how to improve our tools for generating these type of parse trees and how they can be useful for downstream applications. Next up is speech and multimodality, with 72 submissions. The most obvious application of speech is automatic speech recognition, or ASR. In the opposite direction, there are also models to synthesize speech from text. Speaker diarization is figuring out which speaker is speaking at which time, which will be useful if you're trying to transcribe a meeting. Speech is actually a very big area in NLP research, but historically they have submitted to different conferences, which is why there are not that many submissions in the ACL conference. A different type of multimodality is incorporating images. For example, multimodal embeddings try to learn a joint space to represent text and images so that an image and a text that is similar to an image will be close together in this space. And one model that does this is the OpenAI Clip model. By the way, if you made it this far, please do me a favor and smash the like button to feed the YouTube algorithm, and subscribe to my channel. The next topic is sentence level semantics with 81 submissions. Previously, we talked about lexical semantics, which deals with the meaning of individual words. In contrast, here we are trying to understand meaning on a sentence level. For example, a model that turns a sentence into an embedding vector. And these embeddings may be used to compare the textual similarity between sentences. Another important problem in this topic is natural language inference, or NLI. NLI tries to understand the relationship between pairs of sentences, the first sentence being a premise and the second sentence is the hypothesis. And the model tries to classify what is the relationship between the premise and the hypothesis. Does the premise entail the hypothesis? Is it neutral, or do they contradict each other? In this example, if you read the sentences, you will find that this is an example of a contradiction. Next up, we have Multilingualism and Cross-Lingual NLP, with 85 submissions. A multilingual model is a model that can handle multiple languages in a single model. For example, a model that can embed sentences in different languages in a single vector space. Another example of a multilingual model is one that can train on multiple languages at the same time. This increases the amount and diversity of training data compared to just training on one language at a time. Many other tasks can be adapted to involve multiple languages. For example, multilingual NLI is when the premise and hypotheses are in different languages, and as before, the model is trying to classify them as entailment, neutral, or contradiction. Notice that machine translation is usually not included in this category, and we will consider it as its own track. Next, we have information retrieval and text mining with 94 submissions. Information retrieval is basically what powers search engines. The user enters a query, and the model needs to return a bunch of results from a database, oftentimes with millions of documents. The most common way to do this is in two stages. The first stage is a simple and fast model, like keyword matching or vector similarity, that can quickly retrieve from millions of documents. And only after we've reduced the number of documents to a more manageable number, a slower and more accurate model is applied to re-rank the documents in terms of relevance to the query. Next up, we have sentiment analysis, stylistic analysis, and argument mining with 107 submissions. This category includes a bunch of closely related things that we might want to know when analyzing a social media post or any other kind of text. The most basic is sentiment analysis. Is this post generally positive or negative, or is it representing any specific emotions like happiness, sadness, anger, or so on? You may also want to detect the style of the post. Is it casual or formal, and is it written for a general audience or a technical audience? Could the author be experiencing mental health issues like depression or anxiety? Is the post related to politics, and if so, which political party does the author support? And finally, stance detection is classifying how does the author feel about a specific topic, like startups. All of these questions and more can be answered with sentiment analysis and stylistic analysis models. The next topic is somewhat related to this one. It is computational social science and cultural analytics with 113 submissions. This topic is about using large amounts of natural language data to study social issues, like using social media posts to analyze how people feel about climate change over time. It can also be used to study linguistic issues like semantic shift, which is when the meaning of a word changes over time. Another application is digital humanities. A researcher studying English literature might want to analyze all of Shakespeare's works and how his style has changed over his lifetime. These sorts of applications and more are available when we have models that can quickly read over millions of words of text. Next up is summarization with 139 submissions. Summarization is creating a summary out of a document, and there are two ways of doing this: extractive and abstractive summarization. Extractive summarization is when you create a summary by taking out pieces or excerpts out of the original document to create the summary. On the other hand, abstractive summarization creates a summary by rewriting the original document entirely, and this generally produces more fluent text than extractive summarization. These two methods may be combined together in a hybrid approach. First, an extractive model is used to create a summary out of pieces of the original document, and then a second abstractive model is used to rewrite the summary into something that's more fluent. Summarization may be applied to a single document, or it may be applied to summarize multiple documents into one summary. The next topic is language grounding to vision and robotics with 147 submissions. Language doesn't just exist in a vacuum, it actually describes objects and events that happen in the real world. So language grounding tries to connect language with the world in some way. The most basic example of this is image captioning. Given an image, generate a natural language description of the image. Another example is visual question answering, where the model must answer questions related to an image. For both of these tasks, images may be replaced by video, so captioning video or answering questions about video as well. A third method of grounding language to the real world is training a model to follow instructions. This is typically done in a simulated robotics environment where the instruction is given in natural language and the model must generate a sequence of commands that execute the instruction. And the goal of this type of work is to learn to follow instructions in a structure that it hasn't seen before. The next topic is generation with 175 submissions. This is a fairly broad topic, and generation is anything that produces language as opposed to just passively understanding language. Most models generate text by generating one word at a time, and there are many ways to do this. One popular algorithm is beam search, which generates sequences that have the highest probability. Beam search is deterministic and accurate, but the downside is that it is a little bit boring, and it is a preferred algorithm for some use cases like machine translation. If you want to learn more about beam search, check out my video here about how it is implemented. Another approach is sampling, where the model randomly chooses between a few top candidate words. This is non-deterministic, but more creative, and the preferred approach for some applications like ChatGPT. Two of the most popular sampling algorithms are top K sampling and nucleus sampling. Some applications may have further constraints on the structure of the language that you want to generate. You might want your generated text to follow a certain syllabic structure, like when you're translating a song from one language to another. Generation is a broad topic, and research in this area may be applied to any case where you want to produce language, including summarization, machine translation, dialogue, image captioning, question answering, and more. Our next topic is interpretability and analysis of models for NLP, with 189 submissions. A major challenge with neural network models is that they basically are a black box. They might perform very well on some tasks, but we don't really know what they are doing to achieve the result. Probing is a type of model interpretability that tries to understand the internals of a pre-trained models by conducting careful experiments. For example, on the left, by visualizing the self-attention layer and correlating them with different types of syntax structures. Another way of probing is examining the layers of models and seeing whether different layers perform better on tasks than others. Another line of research in this area is explainability. After the model has made a prediction, can we explain why it has made this prediction and not something else? One way of doing this is training a model to generate an explanation of a different model using natural language. A different approach is using saliency maps, which is a gradient-based method that highlights which part of the input is most responsible for making a certain prediction. Next, we have question answering with 197 submissions. In question answering systems, the question is usually just one sentence, but there are many different ways we can produce an answer. One of the most basic ways is extractive question answering, where the model is given a passage. The passage may be just one sentence or several paragraphs of text, but it is set up so that the answer is always a span in the passage. And the SQUAD dataset by Stanford is a commonly used dataset for extractive QA. But this type of model can only produce very short answers, and a more versatile approach is generative QA. Here, the model takes in a question and generates an answer, and the answer can be much longer and can be on any topic. Question answering systems may also involve structured data. For example, if your data is stored in a SQL database, then a good approach might be to convert your question into a SQL query and then generate a natural language response from the results of that SQL query. Finally, the structured and unstructured methods may be combined together in a hybrid approach. First, the model uses a question to retrieve from an external knowledge base using keywords or vector index, something like that. And then a second text generation model is used to generate the answer. So question answering has a lot in common with information retrieval systems. And this retrieval approach has become very popular recently for question answering and chatbots with retrieval augmented LLMs. Next is machine translation with 198 submissions. This is models to translate sentences from one language to another, and it's often the first thing that people think of if you mention natural language processing. The simplest translation models are bilingual models that translate between one language to another language. Like one model might translate from English to Romanian, and another one translates from Italian to English. The downside is when you want to support a lot of languages, it requires pivoting through English, so translating it to English first and then to your second language. A more recent approach is many-to-many models, which means you have a single model that can translate between any pair of languages. This type of model is larger, but there is only one model, so it does not require pivoting through English and losing some quality by doing so. Some many-to-many models can handle as many as 200 languages in one model. One area in machine translation work is how to deal with low-resource languages that do not have a lot of training data. But some of these low-resource languages have neighboring languages that are high-resource, like Uzbek is closely related to Turkish, a language with a lot more speakers. If the model is able to share the information between these two languages, then the translation quality will be better. Another topic in translation research is bytext mining. To train a translation model, you need a lot of parallel sentences, or sentences that mean the same thing in two languages. But there's not that much data available that consists of sentences that are translated to another language. So a more scalable way to get more data is by mining these parallel text from monolingual corpora, like the internet. This is done using multilingual sentence embedding models to find corresponding sentences that mean the same thing, followed by some post-processing to filter out the low-quality sentences. And a fun historical fact, machine translation is generally considered to be the oldest problem in natural language processing. This is a photo of the computer that ran the first natural language processing program, and it translated Russian sentences to English. It was done in 1954. And the transformer architecture, which is used everywhere in NLP today, it was originally designed for machine translation in the Attention is All You Need paper from 2017. So we can see that new models and new methods are often first applied to machine translation because it is such a widely studied and relatively clean to work with problem. Next is resources and evaluation with 213 submissions. In machine learning, we like to have a lot of benchmarks where different models are ranked on a leaderboard according to their performance on some kind of task. And as a community, we like to see how the performance of different models improve year after year, so that we know if they're getting better or if they're reaching a plateau. A lot of work has to go into designing such a benchmark. First, it has to be designed to encapsulate some kind of real-world task and be representative enough while being self-contained. Then there's the actual work of collecting the data from various places and doing the annotation, which could involve hundreds of human annotators. And then, of course, doing QA on these annotations to make sure that the quality is acceptable. And then it should include some baseline models to show how well do the existing models perform and how else do humans perform on these tasks. And ultimately, there is a cyclic pattern to how benchmarks are designed and how they impact further work. Oftentimes, a few years after a benchmark is released, we have models that do very well on the benchmark, but they do not entirely solve the underlying task that it's supposed to represent. And this leads the community to come up with new datasets and new benchmarks to remedy the problem. The blue score, for example, is a common metric used to evaluate many types of generation, including translation. It is relatively simple and fast, and is based on n-gram overlap with a reference sentence, but it is easily gameable. And what this means is that a model can score very high on a blue score, but it could be complete garbage. And researchers have long realized this, and many people have proposed different ways to improve translation evaluation. One of these proposals is BERT score, which uses a language model to evaluate the similarity of an output sentence with a reference sentence. And this has been shown to have high correlations with human judgments. Next is large language models with 252 submissions. This is a fairly new topic, and I believe this is the first year that large language models has been its own topic in ACL. And obviously, ever since ChatGPT, it has exploded in popularity. LLMs share a lot in common with other types of models, but there are a few things that are kind of unique to LLMs that I'll mention here. First is RLHF, or Reinforcement Learning with Human Feedback, which tries to align a large language model to be more useful to humans. Because the initial language model is trained to predict the next word in a sequence, and it's not trained to really answer the question or be helpful. And we have to fine-tune this model with supervised fine-tuning or reinforcement learning to make it more useful. And what's the best way to do this is a topic of ongoing research. A second research topic in large language models is emergent behavior. And emergent behavior is when the model learns to do things that it's not specifically trained to do in its training set, like add numbers or transliterate words to IPA or scramble or unscramble words. And we often find that there is a certain point where above this number of parameters, the model is suddenly able to do this task, and below it, it is not better than random at this task. And there is a bunch of research that tries to explore why this is happening and what type of behavior requires how many parameters to emerge. A third and trending topic in LLM research is scaling laws. So imagine you're Google or OpenAI and you're training your large language model, and you have a fixed number of GPUs and data size, and you're trying to figure out how big of a model, how many parameters should I train? Normally you would just do a hyperparameter search, but with these very large models, each training run could take a month, so you don't want to do that. And that's when scaling laws is important. It tries to form a relationship between this is the optimal size of a model I should train if I have this many GPUs or this much data. By the way, if you made it this far, please do me a favor and smash the like button to feed the YouTube algorithm and subscribe to my channel. The next topic is dialogue and interactive systems with 269 submissions. Dialogue systems, or more commonly known as chatbots, can be either in text or speech format. They can be designed to have open-ended conversations about any topic, but in many cases, it is useful for them to stay on track and help you complete a specific task. This is called a task-oriented chatbot, and it has several different components. First, it needs to understand what the user is saying using language understanding models. Then it needs to keep track of the state of the conversation. For example, what has the user said and what do we need to ask him next to move on to the next task. And then once the system knows what it should say to the user, it needs to convert that to a natural language. So that's the generation module. So we can see that a dialogue system combines together several different parts of NLP to create a unified system that interacts with the user. That's the overall system. And there are some individual pieces that are kind of specific to dialogue systems as well, such as goal-oriented dialogue. This is kind of similar to generation, but in the context of a dialogue system, the generation module is given information about what it needs to convey to the user. In the case of voice-based interactive systems, there are additional challenges as well. For these types of systems to be useful in the real world, they need to be good at handling interruptions or detecting if the user is confused. These things, like handling interruptions, are not relevant in text-based chatbots, but they're essential for creating a fluid experience in voice-based assistants. Next on the list is information extraction with 279 submissions. And this has to do with anything that transforms natural language into a more structured format so that computers can work with it. The first step in this process is often named entity recognition, so taking a text and recognizing all of the named entities like people or organizations or dates. This information can be used for slot filling. This is when we're expecting to see certain pieces of information in the input, like if the user is booking a hotel, we expect them to provide their destination city and travel date. The slot filling system constructs a structured piece of data from the user's unstructured input, and this will be a useful component in a chatbot application. Another type of information extraction is relation extraction, so this comes after named entity recognition. After the model has understood that Microsoft is an organization and Bill Gates is a person, now it needs to understand that the relationship between these two entities is that Bill Gates is the founder of Microsoft. And here's a more complex example of understanding of medical transcript. So the model needs to understand all of the symptoms, the treatments, and the diseases that were mentioned, as well as the timing information and the order that things happened, so it can piece together a timeline of what happened in this transcript. Next up is the second most popular topic, machine learning for NLP, with 313 submissions. This topic deals with more general machine learning methods that aren't directly tied to any specific topics in NLP. And since they're so general, they can be applied to basically any problem in NLP as well as other domains like computer vision. One example is optimization. So this is methods to train your neural network using gradient descent, or find the best hyperparameters or the best neural architecture for your network. Adversarial attacks are when you can perturb the input in some way to create an unexpected result in the neural network. For example, someone recently discovered that if you add a specific string and append it to your prompt, you can bypass the safety filter for a lot of language models. So more research is needed to study how these attacks work and how to defend against them. Few-shot learning and meta-learning are techniques in machine learning that allow you to train a model with very few examples. And domain adaptation is learning the distribution of your input samples so you can detect if an input is out of domain, or train it to adapt to the new shift in distribution. And finally, the topic with the most number of submissions is NLP Applications with 354 submissions. In this video, we've covered lots of different topics in NLP, and they can be applied to many different applications, including healthcare software, e-commerce, grammar correction and writing assistants, language learning, chatbots, recommendation systems, and more. These are typically papers written by people in the industry who are applying NLP in their products. And they are interested in models that are efficient enough and robust enough to be used in real applications. And one topic that is especially important in the industry is making models that are efficient during inference. Some techniques to do this include quantizing the model to run on fewer bits, pruning the network into a sparse network, so cutting out some of the neurons, and knowledge distillation, which is taking a larger model and using it to train a smaller model that is more efficient. If you want to learn more, I have a video here that talks about efficient NLP techniques in a lot of detail. So that's it for the map of NLP. Which of these topics is your favorite or least favorite, and why? Let me know in the comments. And finally, please remember to like this video and subscribe to my channel to receive more machine learning videos. Goodbye!